All right, so I wanted to talk about discrete time dynamical systems. We're going to be talking about this for more than one video, but let's go ahead and introduce it. So a discrete time dynamical system is what happens when we measure one or more variables at regular time intervals. So discrete time, we normally think of time as being continuous. But, for example, if I track the weight of some child by measuring their weight every single month after birth, that means I measure the variable of weight every month. So I've measured something at regular time intervals. Congratulations, this is a discrete time dynamical system. All right, some comments on notation. So let's just all use what's most common. When I'm measuring something with respect to time, typically I would use T for time, and then I would just let the reader know this is in months. And then the variable name that I give to the thing I'm tracking, which in this case is weight, normally the capital letter is going to represent what you're tracking. So I want to use capital W to be weight, but I give it a subscript. So I would do W sub T to let the reader know that I'm tracking this with respect to time. So for example, my first measurement of this newborn baby being 7 pounds would be called W sub 0. 1 month later, this child weighs 9.2 pounds, and that would be W sub 1. Then I have W sub 2. There we go. And then W sub 3 and W sub 4. And my question is, what is a good guess for what W sub 4 should be? So go ahead and pause the video and try and work that out. Okay, so let's see. What can we do? Well, if you're like me, you are looking for patterns in these numbers. And in other words, we are going to ignore the month data, and we look entirely in this column here. Okay, so what are some things we might notice? We might notice that going from W0 to W1, the child gains 2.2 pounds. And same thing happens going from W1 to W2, and going from W2 to W3, and W3 to W4. Well, we don't know, right? But that's what we're trying to guess. And so maybe a reasonable guess would be that we're going to gain 2.2 pounds. And if that's what happens, then we can fill in our guess, and this would be 15.8. Okay? And yeah, I do think that's a reasonable guess. So I think this is a question that many of you, if not all of you, could probably approach, and you came up with some kind of guess like this. But now we want to mathematize it. What a word. And let's write down, for example, this type of relationship. And there's different ways we can write it. So one way is what's called a difference equation. So when you're tracking something at regular time intervals, you can just take the difference between two successive measurements. So one measurement would be W1, and W1 succeeds W2. W1 succeeds W0. W0 precedes W1, but whatever, these are successive measurements. Gosh, what a mouthful. I'm totally making this harder than it has to be. Their difference is 2.2. W2 minus W1, their difference is 2.2. W3 minus W2, their difference is 2.2. So equation, the word equation in math kind of has the same root as equal, and it's because an equation is going to relate two things via an equal sign, and that's how we get an equation. Okay. Now, we don't really use this term in this class, but I want to introduce it because, one, I prefer it to the term we use. The term we use is updating function. And the other reason I wanted to introduce the term difference equations is because some of you might go on to take a course called differential equations, okay, which is when we're relating how things change to what they are, okay? That's pretty vague and hand-wavy, but I think it would set the stage a little better for your future. And in fact, later on in this course, we're going to see some very simple differential equations, a very special cases. Okay, so what's an updating function? It's what happens when you solve for the later variable. So W1 is later than W0. The weight at month 1 occurred after the weight at month 0. So if I solve for it, I have W0 plus 2.2. Similarly here, I could say W2 is W1 plus 2.2. And W3 is W2 plus 2.2. Okay, and the general form that these have, so the general form of my difference equation is that the weight of the child the next month, the successive month, minus the weight at the current month is 2.2. Whereas in updating function land, we would say the weight of the child next month is equal to the weight this month plus 2.2 pounds. Okay? So, what do I want to emphasize about an updating function? It's that its input is the variable you're tracking. In this case, it's my weight at month M, and its output, it's still the variable you're tracking. It's still weight, it's just at a different point in time. So in other words, the updating function does not concern itself with the month data explicitly. The updating function is what happens where your input, for example, is this, and your output is the next value in the same column. In this case, it's the weight column. In general, it's whatever you're measuring. So let's go ahead and graph the updating function. Okay, so here we are. Let me slide this over a little bit. Okay. All right. So if I graph my data points of an updating function, what does that mean? So remember, my input is Wm and my output is Wm plus 1. Let's go ahead and label some axes. This axis here, and all these numbers, they all are weight at a given month. So this is in pounds, not that it really matters. And my vertical axis is also weight. It's just a month later. So for example, my child began at 7 pounds, and a month later it weighed 9.2 pounds. So this first dot is saying if you start at 7 pounds, a month later you'll be 9.2 pounds. That's what this first dot is saying, but I could also label it in general and call it W0, W1. Okay? Or I could have called it 7, 9.2. Doesn't matter. Here I have W1, W2, which is if you weighed 9.2 pounds, then a month later you're going to weigh 11.4. Okay? And this other dot here is W2, W3, which just says if you weighed 11.4, then a month later you're going to weigh 13.6. All right. So this plot where I'm relating months, I'm relating weights for given successive months. I'm starting to plot points on my updating function, but let's find, or let's graph the whole updating function, which I'll just abbreviate as UF. Graph the whole updating function. Well, you know, look, we have this expression for it. And W sub m is my input. W sub m plus 1 is my output. And we are used to an input being called x and an output being called y. And so what a lot of students find helpful is when they see an equation for an updating function, their brain just converts it. And they say, hey, what this is saying y is equal to x plus 2.2. And in fact, okay, y equals x plus 2.2. Let's talk about this line for a moment. It has a slope of 1, and it has a y-intercept of 2.2. And if I go back here to my data, let's see, 2.2 is probably around here somewhere. And so let's see if that's indeed what's going on. If I start at this point, and I go and connect to the last point, and just hold, boom, there we go. Yes, indeed. This, right, it all works out. My Wm plus 1 equals Wm plus 2.2. That is my updating function. And I can graph this updating function as my blue line here. The individual data points I have are just these data points for my child for this, 3-month or however long period. Okay, so that's what an updating function is. Now, let's assume that this trend continues, okay? Let's assume that it continues maybe for the first 2 years. Is that reasonable? I don't know how many months. There's 12 months in a year, so that would be 24 months go by. And if this trend did continue, then in 2 years, let's see, if I multiply this by 2.2, that's 48 plus 5, that's about 52 pounds. So my 2-year-old baby would weigh around 60 pounds if I did that right. I don't know. Yeah, that might be reasonable. I don't know. Children. Okay, so I can ask you, assuming this continues, assuming trend continues, what is the baby's weight at, we'll say 20 months. 20 months. Okay. All right. So pause the video, try and figure that out. What is the baby's weight at 20 months? Okay, so this question of 20 months, we have multiple ways to approach it. One possible way is I continue this trend. I say, well, at month 5, I have to add 2.2. At month 6, I add 2.2. At month 7, I add 2.2. And I just continue this until I get to 20. Another way is to find a function. Find a function that will, if I give it as an input, the month, it will output the weight at that month. At that month. In other words, I need to find a function where if I give it m, it will output w sub m, right? W sub m stood for the child's weight at month m. And, oh, oops, I had switched around. Sorry, I previously was using m for months on a past attempt of this video. Here we go, but now I'm using t for time, but it's measured in months, right? Okay, I got t, w sub t. Oh, that's why. All right, I'm sorry. I hope this all made sense. This should say t plus 1, or, you know, maybe I should just go back here and say, let's just call this m for months. Okay, now everything works out, and I can go back to just using that. I'm sorry, but I believe, and hopefully it all still makes sense. So, okay, if I tell the person how many months, then this function or this person will tell me the weight of that many months, which means I need to plot this relationship, okay? This plot, my input is w sub m. It's not m. So I have a completely different graph to look at. All right, so instead of doing this counting strategy of find weight at month 5, then 6, then 7, then 8, then 9, then 10, 11, blah, 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 I want to do this much more efficiently. All right, so let's do that. I need to get rid of this stuff. And let's just downsize you. In fact, we'll just delete you. And now we want to look at you. All right. So here we go. Now I have a plot. I want to keep it on the foreground. We might just have to insert the paper. We'll just make it a little lower, put it here, and zoom in. All right. Now I have a plot where my input axis is the months, okay, m. And my output axis is w sub m, right? I have a different input, different output than before. And so on month 0, when this child is first born, it weighed 7 pounds. So I have the 0.07. At month 1, this child weighed 9.2 pounds. At month 2, this child weighed 11.4, and so on. Okay, so in other words, now I'm looking at both columns of data. Before, I could cross out the month, and I just looked at the pattern here. But now I actually want to use the value on the left to get the value on the right. Okay. All right. Well, you might look at these points and say, gosh, it looks like they lie on a line. And you could test it out, and you'd be correct. I just want to demonstrate a general strategy for trying to find this equation. So here's the idea. What we want to do is use, in this case it'll be w sub 0, to find w3, or, I'm just picking something later on, without simplifying. Okay, so this is just a general tip when you're trying to find a solution function, which is ultimately what I'm going to try and do right here. I'm going to try and find this function, and this is called a solution function. Solution function. Okay. All right. So this seems like a really weird, vague statement, and that's because it is. So here's what I mean. We have our month, and we have our weight at that month. And I know that I began with 7. All right, now, I say without simplifying. And what I mean is, in month 1, the child's weight is 7 plus 2.2. So I'm not going to write 9.2. I'm going to write the way I would find that weight. In fact, here, let me add, we're going to find the weight at month 1, the weight at month 2, and the weight at month 3, using my beginning weight and without simplifying. Right, so okay, I have to add 2.2. Now my weight at month 2, I have to add 2.2 again. And that's where the 11.4 comes from. My weight at month 3, I have to add 2.2 again. Okay, and there's nothing special about me saying do this for 1, 2, and 3. In general, you might have to do it more times or less times, but the second step is to express the pattern as a function of the first column. Okay. And again, like, these are kind of just weird, vague steps, but hopefully it'll make sense with the demonstration. All right, so there's a pattern going on. All right, there's this sort of increasing progression. Oh, I didn't write the last. Plus 2.2. I need to express that pattern as a function of this first column here. So often, after we've written everything out, we want to rewrite it using more compact mathematical notation. And here's all I mean in this case. Let's get another color. So this is the same as 7 plus 2 times 2.2. And this is the same as 7 plus 3 times 2.2. And this is the same as 7 plus 1 times 2.2. And this is the same as 7 plus 0 times 2.2. And I'm just doing this because I'm just trying to find a pattern that makes my output, my column over here, a function of my column over here. Okay, so hopefully you see that if you give me an m, so if you give me a number over here, which I'm calling m, then my output is going to be 7 plus m times 2.2. Okay, right? If I had a 4, I'm going to do 7 plus 2.2 plus 2.2 plus 2.2 plus 2.2. So I've added 2.2 4 times. This is the same as 7 plus 4 times 2.2. Okay, and this right here, this is the function that's graphed. This is my solution function. It's the thing where now it's very easy to answer my previous question of what is the child's weight at 20 months, assuming this trend continues, right? So now if my m is 20, then my weight at 20 months is going to be 7 plus 20 times 2.2. And that's around 60 pounds. And yeah, if I were to graph this function, all right, look, what's my input variable? It's m. What's my output? It's, this expression. But we're used to, from all of our lives, it being drilled into us, calling the input variable x and calling the output variable y. And so what you might be used to is to say y is equal to, okay, so m is being called x, So in the form we're most comfortable with, it's 2.2 times x, that takes care of that part, plus 7. Okay, so these data points lie on the line 2.2x plus 7. And yeah, if I were to just kind of go for it, I don't know, maybe about there. All right, so this is a graph of my solution function. The solution function has an input variable, which is the original time variable. In this case, that's months. It might be seconds. It might be years. It might be days. But it's the original time variable, and its output is the thing we've been measuring. A solution function will go from here to here. Solution function. An updating function goes from here to here. Okay? So it's just a matter of what's your input, what's your output. But this is also why I prefer the term difference equation, because to ask what is the difference equation, your brain doesn't have to worry about which function is he talking about. When I say what's the difference equation, I mean describe how my measurements are changing. Take their difference. That's literally all I'm talking about. And so if you're later asked to find the updating function, just find the difference equation and then just rewrite it. Okay? All right, so that's our first variable. Our first example. I've beaten that to death. I'm going to stop the video here, and then we'll pick it up next time doing this again for more complicated systems.